Hello, my name is Mikhail Karasikov. In this talk, I'm going to present our work on topology-based sparsification of graph annotations. This is a joint work with Daniel Danshu, Harun Mustafa, Ander Kalis, and Gunnar H. The Bruijn graphs are commonly used for indexing sequence data. To represent metadata, such as source of each sequence, each k-mer is extracted from the sequence and labeled in the graph. These labels can represent reference genomes, SRA experiments, or something else. All the k-mers are then stored in a k-mer dictionary that allows searching by k-mer, and the relation between the k-mers and the labels is stored in a binary matrix. These two components represent an annotated Bruijn graph. For large sequence collections, the annotation matrix may include trillions of rows and millions of columns, which makes it not trivial to represent. I should also mention that there are other approaches for representing annotated Bruijn graphs, such as those using Bloom filters or other approximate membership data structures. They usually build a joint data structure that encodes both k-mers and labels, but I will not cover those approaches in this talk. Different methods can be used for representing the annotation matrix. For example, the columns of the matrix can be stored independently and compressed in SD vectors or other succinct bitmap representations. For better compression, one can represent the matrix as a binary relation with every tree, where the empty rows are erased from the matrix and the columns are grouped by their similarity and compressed using the same technique on the next levels. Alternatively, for faster queries on rows, all of them can be concatenated into one long vector, represented in a succinct data structure. We call this representation row flat. This was first used to represent the annotation matrix in Vari. On the other side, the rows of such matrices repeat very often, and Rainbow Fish takes advantage of that and builds a dictionary of unique rows and compresses them with a technique similar to row flat. Last, Mantis MST improves Rainbow Fish by representing the unique rows in a minimal spanning tree structure, storing only the differences between similar rows instead of their original bits. But still, same as Rainbow Fish, it has to store a vector for mapping rows of the original matrix to unique rows. And therefore, we call this method Rainbow MST, which includes the rainbow mapping vector and the MST part. We notice that even though the unique rows are represented extremely efficiently in MST, the bottleneck of this representation is actually in the mapping vector, which takes significantly more space than the MST itself. We built a method which directly uses the topology of the annotated graph and doesn't require a mapping vector. We observed that adjacent nodes in the graph often share similar annotations. So the idea of this method is to store only the differences with diffs of the labelings of adjacent nodes computed as exclusive OR on the respective rows of the annotation matrix. For example, these two nodes have exactly the same annotations, therefore the diff is a zero row. The next two nodes have annotations that differ only at label 3. Then we apply the same rule for the first two nodes. For the nodes with multiple outgoing edges, we only pick one of them to define a single RowDiff successor against which we compute the diff. We simply pick the lexicographically smallest adjacent node as a successor, and then we compute the diff. Finally, for the nodes with no outgoing edges that are called sinks, there are no successors and therefore must store their original rows. We call such nodes anchors and mark them in an extra bit vector. So we see that this method effectively transforms the matrix, makes it sparser and more compressible. At the same time, any generic matrix representation scheme, such as multivariability or row flat, can be used on top to store the transformed matrix. And finally, the overhead is very small. It's less than 1 bit per node to store the bitmap indicating the anchor nodes. To reconstruct the original annotation for a node, we reconstruct the original annotation first at its successor and then add the diff at that node. And the original annotation for the successor is reconstructed recursively. Formally, the algorithm for reconstructing original annotations is shown here. Two conditions must be met in order for this algorithm to reconstruct the annotations correctly. First, as already mentioned, all sync nodes must be anchored and store their annotations in full. Secondly, RowDiff successor can happen to build a cycle in the graph. And each of these cycles must have at least one anchor node in it. To demonstrate this, let's consider the following example with a RowDiff cycle. If you want to reconstruct the annotation at this node, we follow the successors and see that the algorithm will never terminate unless there is an anchor node in the cycle. Finally, we are going to require that each node in the graph has an anchor node within about the distance from that node. We require that to ensure a constant time query complexity. Based on that, we propose the following algorithm for anchor assignment. First, for each node with at least one outgoing edge, we pick a single successor node. Second, we mark all sync nodes as anchors. Next, we reverse tighten the sync nodes from the picked edges backwards. If a node is not a RowDiff successor for its adjacent nodes, we terminate the traversal. For example, this node is not a RowDiff successor, so we stop the traversal there. Next sync is a RowDiff successor, so we traversal on the edge, next, and next. When we reach the nth node from the last anchor, we set a new anchor there to satisfy the maximum RowDiff path length restriction. And then we continue the traversal same way. To this point, there are no RowDiff paths longer than our predefined threshold m. In practice, this step covers the vast majority of the nodes in the graph. The algorithm is also very easy to parallelize. And finally, what's left are parts of the graph that end with a RowDiff cycle, which we process with a special algorithm in the next slide. To cover all paths that end with a cycle, we start the traversal at unvisited nodes and traverse forward until we reach a visited node. We make this node a new anchor. We also make anchor every mth node in that path. Then we repeat this process until every node in the graph is visited. Now we see that sometimes this algorithm creates unnecessary anchor nodes. To avoid that, we mark every node in the previously visited path as near anchor. And when another path merges into a node marked as near anchor, we know that it already has an anchor node close to it, and therefore we don't create a new anchor there. However, this time, we don't mark the last predecessors as near anchor, since they may be in the distance of up to 2m from the next anchor. This algorithm processes the remaining part of the graph and ensures there are no RowDiff paths longer than 2m. Once all successor and anchor nodes are assigned, we perform the actual RowDiff transform. The original annotation matrix may take up to 10 terabytes even when compressed and not fit in RAM. We therefore developed a scalable and efficient algorithm which transforms the original matrix by columns in batches. First, we pre-compute all successors and predecessors for all nodes in the graph and store this array on disk. We do this so we don't need to keep the graph in memory when transforming the columns in the next steps. For the next step, we load the next batch of columns from disk and transform all of them in parallel while reading the pre-computed successors and predecessors from disk. Note that all the columns can be distributed over multiple machines and transformed in parallel. This enables us to transform virtually arbitrary large annotation matrices. We implemented RowDiff within the metagraph framework, which provides all other components for representing annotated genome graphs, such as succinct graph representations, different annotation representations, lower-level data structures such as hybrid bit vector representations. We also used bitmap representations from the succinct data structure library. We evaluated our approach on two types of data. The first dataset contains 10,000 RNA-seq experiments previously used for evaluating the Mantis MST method. The second dataset contains all fungi sequences from RefSeq release 97. The first dataset contains reads from 10,000 different sequencing runs and therefore includes significantly more variation. The reference sequences, on the other hand, build a graph which mostly consists of linear paths and therefore is expected to compress better with the proposed RowDiff method. In the first experiment, we look at the dependence of the compression ratio on the k-mer size. The compression ratio is defined as the ratio between the size of the annotation matrix before and after the row-diff transform. We see that, as expected, using longer k-mer makes the graph sparser and thereby increases the compression ratio of row-diff. However, setting the k-mer size to 23 and above makes the graph sufficiently sparse to enable a good compression ratio. And for RCEQ, it achieves over 30x compression. In the next experiment, we check how the maximum row-diff path length threshold M affects the size of the annotation matrix. The column M equals 0 represents the original untransformed annotation. We see that using larger values of M increases the compression ratio. But at the same time, setting M to 50 enables a very good compression, which doesn't improve much with higher M for the more complex RNA-seq graph. Next, we compare the representation size against the state-of-the-art methods, multi-bubble T and rainbow MST. We apply the row-diff transform and use two different representation schemes to encode the transformed annotation matrix, row-diff and multi-bubble T. These curves are shown in red and purple, respectively. We see that row-diff multi-bubble T is significantly smaller than rainbow MST on both datasets, and row-diff performs especially well on the sparse RCEQ graph and outperforms rainbow MST by almost 30 times. Again, we see that the size of the rainbow MST representation is actually dominated by the rainbow mapping vector, which alone is larger than the entire row-diff multi-bubble T representation. We look at the compression ratio for individual columns of the annotation matrix. We see that it's significantly different for different columns, but most of the weight is concentrated around 2x and 60x compression for the RNA-seq and RefSeq graphs, respectively. This graph shows the total construction time required to perform the row-diff transform and to convert the transformed matrix to the multi-bubble T representation with 30 threads. Unfortunately, the rainbow mapping vector in Mantis MST by design is constructed together with the graph, and extracting the time required to construct the mapping vector alone, it wasn't possible. So in order not to overestimate the construction time for the MST method, we decided to look at the lower bound, the time taken to construct only the MST part without the mapping vector. However, despite the fact that the construction time for rainbow MST is significantly underestimated, we see that it's still larger than the full construction time for our method. Also, row-diff construction time grows linear with the number of annotation columns and grows superlinear for MST. This demonstrates the scalability of row-diff and makes it especially valuable in large settings. Here we compare the query time. Similar to the previous work, we queried 100 and 1000 random human transcripts in the annotated graph constructed from the RNA-seq data. We see that for querying a sufficiently large batch of sequences, here 1000 transcripts, all methods have performance in the same order of magnitude, and the difference may be neglected in favor of the high scalability. Another thing we can see from this table is that row-diff actually improves the query performance, presumably by making the matrix sparser, which becomes faster to query in a multi-bubble T representation. Finally, we look at the choice of the maximum row-diff path length threshold and how it affects the query performance. We see that the graph traversal time makes up a negligible part of the total query time, even despite the fact that we used a succinct graph representation with slower traversal. There is no noticeable effect on the value of M on the query time when the transformed matrix is encoded in the row sparse representation, and for multi-bubble T, surprisingly, queries become even faster for larger values of M. To conclude, we've presented RowDiff, and we've shown that it's a powerful technique for sparsification of graph annotations. It acts as a transform of the original annotation matrix and makes it sparser and more compressible. At the same time, it's compatible with generic schemes for sparse matrix representations, such as column measure, row flat, row sparse, and multi-bubble T. It enables higher compression than state-of-the-art, more precisely 30% higher compression for RNA-seq graph, and 26 times better compression for reference sequences. And finally, it scales to very large graphs. Thanks for your attention, and thanks to the Swiss National Science Foundation for funding this work.